In this video, we'll be exploring the concept of temperature and steady-state heat flow. We will start by outlining the objectives for today's session. To further gain an insight, we'll be explaining Newton's law of cooling, heat transfer by conduction. Here we'll be applying Fourier's law of heat conduction. Newton's law of cooling states that the time rate of change of temperature of a body is proportional to the temperature difference between the body and its surrounding medium. Now, how can we further gain an insight or in-depth knowledge of this concept? Recall, when we were studying exponential growth in our previous video, for example, the spread of a pandemic, we said that the rate of change is proportional to how many people that were infected. This implies that the rate of change was proportional to the number of quantity of a variable. But now that doesn't seem quite reasonable here. For example, if the temperature in my cup of tea is very close to the ambient temperature, I wouldn't expect a very rapid change. But if the temperature was way above the ambient temperature, then I might expect a rapid change. What does this entail? This further implies that in this case, we will say that it is proportional to the difference between the temperature of my cup of tea and the ambient temperature. The key word is the difference. That is the game-changing word in this concept. So simply put, a glass of hot water will cool down faster in a cold room than in a hot room. Hence, we say that Newton's law of cooling is formulated as dt all over the t, which is proportional to t minus t subscript m. Now, to further get this, you need to understand that if something is much hotter than the ambient temperature, then the rate of change should be declining in temperature quickly. However, if it is much cooler, it should be increasing in temperature quickly. Let's delve into the concept of heat transfer by conduction. Here we'll be applying our Fourier's law of heat conduction. When a temperature gradient exists in a body, there must be a heat transfer from the high temperature region to the low temperature region. The energy transfer by conduction and the heat transfer rate per unit area is always proportional to the temperature gradient. So mathematically, we have that our Q over A is proportional to the T over the X. Now, whenever we have the proportional sign, to remove it, we need to add the constant term. We need to add the constant term and an equality sign. To further break this down individually, we have that the T represents or denotes the temperature difference. The X represents the thickness of the wall. The T over the X, the combined term now, represents the temperature gradient. This is also known as the variation of the quantity with respect to the distance. Recall from our previous video where we delve into the concept of rate of change. When we have gradients, it means change of that physical quantity with respect to distance. So from here we have that our Q represents or denotes the rate of heat transfer. A represents the area of heat flow normal to the direction of flow. K represents a coefficient of thermal conductivity. When we are solving examples on this topic, you'll be appreciating all these variables, especially our area of heat flow normal to the direction of flow. The negative sign satisfies the second law of thermodynamics that heat must flow downhill on the temperature scale. Now let's start by looking at an example in the next video. Don't forget to like and subscribe to our channel.